Hello everyone and welcome back. Today I will be talking about the last part of chapter 3, electronic configuration. I will provide a link in the description of the video for the website where you can download the material. As we have seen before, the electrons are arranged in certain orbitals and the name of the orbital is usually written as symbols SBDF, and the number on the front represents the principal quantum number, and it is also the number of the period in the periodic table. For the number of electrons is usually on the top of the symbol. If you looked at the periodic table, you could see that in the first group it will be filled with S to the power 1, and the last orbital in each one of them will end with the electronic configuration S to the power 1, and the number of period will be written in front of this letter, which means it will be 1s1, 2s1, 3s1, and so on. The second period will be filled with the last electronic configuration will be S to the power 2. This means the S will be filled with 2 electrons and the period number will be written in that side. So 2s2, and this one will be 3s2, and so on. P orbitals will be filled in that part, and the number of the group can be calculated by adding 10 to the number of electrons in p orbitals and the number of electrons in the s orbitals. Of course, the last shell, the last p orbital and the last s orbital. For d elements, it can be also calculated, and that part, it will be equal to the number of the electrons in the subshell d and electron plus the electrons in the subshell s. So the orbitals, the number of the group will be equal to number of the group will be equal to electrons in the d shell and in subshell and the electrons in the s shell. In here you could see that the rule states that if the element belongs to the s block element, its group number will be the number of the valence electron. So I have s to the power 1, so it will belong to the group 1. But if I have s to the power 2, this means it will belong to group number 2. As for B block elements, it will belong to the number of the group will be calculated as 10 plus the number of electrons in last orbital B and the last orbital S. As for D block elements, it will be the group number will be the number of electrons. In that case, for the D, electrons in the last field D subshell and the last field is subshell. Now let's take an example. An element that has electronic configuration. This electronic configuration. Which block in the periodic table does this element belongs to? So if I looked here, I could see that it ends with P subshell. This means this element will belong to the B subshell. So from here I could see that it ends with B. This means that it belongs to B elements. As for which group does it belong to? So now if I want to the number of the group, I can add 10 plus the number of the electrons in the P subshell, which is 5, and the number of electrons in the S subshell is equal to 2. This means it belongs to the group 17, and because if I wanted to identify this element, I have to sum up the electrons. If I sum up the electron, I find it to be 53. If I looked at 53 in the periodic table, I will find it that it belongs to the iodine. Let's take another example. Which block in the periodic table does the element with the this electronic configuration belongs to? If I looked at the last two orbitals, the 3d and the 4d, I could see that the 4s should have been filled before, completely filled before the 3d. But what happens here that I have here 5 electrons in the D. This is why it is half filled. This is why it's been filled before filling the 4s. So that is the only case where I could fill D, 3D before the 4s, because the 3D will be more stable and it will has less energy. This is why this element will belong to the D block element, and the number of the group is equal to the number of the electrons in the D group and S group, which means it is 5 plus 1, so it belongs to group 6. If I try to add electrons to any orbital, I have to follow Pauli exclusion principle or Hund's rule. The Pauli exclusion principle states that no two electrons have the same 4 quantum number. So one of those electrons will actually be rotating in the clockwise, and the other one will be anti-clockwise. For Hund's rule states that no electron pairing happens before each subshell is filled with is half filled, which means if I have here something like carbon and I have here 2 electrons and here 2 electrons, so I have to fill these 2 subshells. But if I looked at the 2p, I have 2 electrons. I cannot put the 2 electrons in here in this orbital, because I have to half fill the 3 orbitals first. So I will fill this with 1 electron, and I will fill the second orbital with another electron. Something like nitrogen, in that case I will fill the first one completely filled, and the second orbital 2s is also completely filled. As for B, the 3 electrons will be separated in 3 orbitals according to Hund's rule. So no electron pairing. I cannot put here 1 electron because I have to half fill all electrons first. For oxygen here, I can, in that case, I can put electron pairs in the same orbital, because now the 3 of them are half filled, but I have 4 electrons, so I have to add another electron, so I have to add it in that case in here. So no electron pairing happens before the orbitals are half filled. Now if I try to write the electronic configuration for ions, if I look here at, I have positive ions and negative ions. The positive ions are the elements that lost electrons, and the negative ions are the elements that gained electrons. In that case, if I try to write something like chromium 3 ion, in that case I know that chromium has 24 electrons. If I try to write the electronic configuration for chromium atom, it will be equal to argon 18. So 18 up till this point, and I have 4s2 and 3d will be filled with 4 electrons. Now if I try to get the electronic, to detect the electronic configuration of the ion, this means 3, I have to lose 3 electrons. So this ion lost 3 electrons. So this ion will lose the electrons from the 4s first, then it will take electrons from the 3d. If it lost 3 electrons, this means it will lose the 4s2, all of it, and the 3d will be filled in that case of 3 electrons instead of 4. So chromium 3 ion will be equal to argon, electronic configuration will be equal to argon 3d3. Now if I looked at negative ion, in that case oxygen negative ion, I know that oxygen element has 8 electrons. So if I write the electronic configuration for oxygen element, would be equal to 1s2 and 2s2 and 2p4. But I have here gained another 2 electrons. This means I have to add another 2 electrons to this shell, and in that case it will be filled with 6. So the electronic configuration for oxygen ion will be equal to 1s2, 2s2, 2p6. Now let's look at the pattern in ionization energies in periodic table across a period. In that case, if I looked across the period and I looked at the nuclear charge, I could see that nuclear charge is increasing. So I'm increasing the number of nuclear charge. You have to remember this is the number of protons are increasing in that side one each time. I'm moving from an element to another element, and at the same time I'm increasing the number of the electrons. If I'm increasing the number of electrons, this means I will have completely shelled electrons in the outer shell from the nucleus. This is why when I move from across the period, now if I lost any electrons, this means the effect of the nucleus, which will increase, will be more effective to attract the electrons to the nucleus, because now the number of electrons are less. Now let's look at this graph to explain what happens to the ionization energy across the period. You could see that there is an increase in the ionization energy from boron to carbon and from oxygen to fluorine. This is in the same groups, but now there is a loss in electrons in the outermost shell, which means increasing the nuclear charge will have a more effective attraction to the electrons in the outermost shell. In general, if I looked at the large difference between the lithium and neon, I could see that there is a high increase in the ionization energy across this period. Now, if I looked at the ionization energy between moving from one period to another period, I could see that is a large decrease. There is a very big decrease. This is what happens. This is a drop between neon and sodium, and another drop I could see it here from helium to lithium. So there is a large decrease in the ionization energy from one period to another. This decrease in the ionization energy from one period to another because I'm adding another subshell. So if I looked at the electronic configuration of the helium and the lithium, I could see that the helium is 1s2, while the lithium 1s2, 2s2, 2s1. Now I add another subshell. This is why it increased, the ionization energy decreased a lot, because now it is easier to remove this electron from this subshell because I increased the number of electrons. You have to remember, if you increase the number of electrons, so electron numbers increase, the ionization energy will decrease. So now I add another shell, so this shell will will be shielded from the electron from the nuclear charge because of being more away from the nucleus. This is why this will have a very big drop between helium and lithium in the ionization energy. So if I looked at this graph again, I could see that although I said that will be increasing in the ionization energy between across the period, I could see that there is a slightly small drop between beryllium and boron, and another drop between nitrogen and oxygen. For beryllium and boron, if I looked at the electronic configuration, I could see that the electronic configuration in that case of beryllium contains 1s2, 2s2, while for boron is 1s2, 2b2, 2b1. I have only one electron in p, so boron would prefer to lose this electron and to have empty p orbitals. This is why the ionization energy slightly dropped from beryllium to boron. Now, if I try to explain the slight drop between the nitrogen and the oxygen, I have to look also at the ionization, the electronic configuration. And the electronic configuration tells me that nitrogen have half-filled electronic orbitals, and for oxygen it have paired orbital, one paired orbital, and two unpaired orbital half-filled p orbitals. In that case, oxygen would prefer to lose one electron and to have half-filled p orbitals than to have this electron. This is why the ionization energy will decrease slightly from nitrogen to oxygen, because it will prefer to lose this extra electron. Now, if I looked at the ionization energy pattern down the group, we said that across the period it will increase, but down the groups I could see that I will add one extra orbital. This increase in the nuclear charge will not substitute the extra orbitals which will shield the nucleus from the outer electrons. This is why I will have a drop in the ionization energy from one period to another. So the shielding by complete inner orbitals will increase, and these two factors, which is the distance increasing and the shielding that happens, will affect the ionization charge, and it will have smaller or decreasing ionization energy. So I will have a decrease in the ionization energy down the group. By that we came to the end of chapter 3. Thank you and goodbye.